Supermassive black holes. Brooding dark giants that can engulf whole worlds.
The universe is full of strange things, but there's nothing stranger than a black hole.
But now, science is on the cusp of solving their biggest mysteries.
Trying to make an image of a black hole is probably one of the hardest things you can think of to do. We're trying to see the unseen.
Could these new discoveries open up incredible opportunities for our species?
Maybe they actually access different dimensions of space and time.
To find out, we will hunt down the biggest, baddest black holes in the cosmos and investigate how their inner secrets could revolutionize our understanding of the universe.
I see black holes as the key arena where we can change the course of science.
In the vastness of our cosmos, there is one mysterious object that is so strange it confounds even the greatest minds. A supermassive black hole.
It can eat up a star, it can eat up a planet, it can eat up a person, or it can eat up another black hole. The black hole will absorb it and grow larger as a consequence.
You know, if you go into one, you're never going to tell your friends about it because you'll never escape.
Black holes are the ultimate prediction of Einstein's most famous theory, relativity. His equations state that anything with mass distorts space and time itself. Black holes have so much mass, crushed into a tiny volume, they bend space and time so far that very strange things happen.
To me, the weirdest thing about a black hole is that it actually can stop time. It can actually collapse space itself. I can't imagine anything weirder than that.
This distortion of space is so extreme, it also makes black holes invisible.
Space and time are so extremely curved and warped around them that there is a place from which even light can't escape anymore, and any light that falls into it is lost forever.
But if Einstein's equations are correct, and black holes are invisible, that creates a problem. We have never actually seen one. So how can we be sure that they exist? Now, scientists are trying to prove once and for all that black holes are real. Shep Dolman is attempting to take the first ever picture of a black hole.
Trying to make an image of a black hole is probably one of the hardest things you can think of to do. If it was easy, everybody would be doing it. We're trying to see the unseen. Even though it's never a good idea to bet against Einstein, it's always a good idea to test and verify.
Shep's target is an area of our galaxy where scientists predict there is a supermassive black hole. Pulling away the dust and haze from the Milky Way reveals a cluster of stars, zooming around its center. These stars can only have such fast orbits if they are circling something with enormous mass, crammed into a very small volume. The best explanation? A supermassive black hole scientists have called Sagittarius A star. Based on this prediction, Shep is targeting the center of the Milky Way. And the galaxy itself presents the first obstacle.
It's not straightforward to try to image the black hole in the center of our galaxy. To see it, you first of all have to pierce all the gas and dust between us and the center of the galaxy. And the best way to do that is to observe in radio waves, which very easily can see through all that gas and dust.
Unlike optical telescopes, radio telescopes can pierce the 26,000 light years of dust and gas that stands between Earth and the center of the Milky Way. But even with the most powerful radio telescope, Shep will struggle to image Sagittarius A star. A black hole is the corpse of a giant star. Once the Colossus runs out of fuel, it loses the fight with its own gravity. The inner core starts to collapse, and the star explodes in a violent supernova. But the core survives and collapses to an infinitely small point called a singularity. This is so dense, it bends the space around it to the point that even light can't escape, forming a sphere of darkness called the event horizon. Sagittarius A star's event horizon is 24 million kilometers across, but it is nearly 250,000 million kilometers from Earth, creating a problem for Shep.
It's equivalent, this is crazy to think about, but using your naked eye to see an orange on the moon. That's the level of magnification we need in order to pull this off. So if you want to make an image of a black hole, which is an extremely small object, you need to build a very, very large telescope. So in order to get the magnifying power required, we would have to make a telescope as large as the Earth itself. Now, it's impractical to scale a telescope like this up to those kinds of dimensions.
For the last decade, Shep has worked on an audacious plan. He's linked radio telescopes around the planet to form a network called the Event Horizon Telescope, and pointed them at the center of the Milky Way at exactly the same time.
With perfect synchronization, at multiple telescopes like this around the globe, we should be able to make very crisp pictures of the region right around the black hole.
The further apart these telescopes are, the more detail he will pick up. If they are spread right across the planet, Shep's network will be 2,000 times more powerful than the Hubble Space Telescope. But even with this much power, how can he see something that by definition is totally black? Shep thinks there might be a way. A black hole itself is invisible, but matter falling into it should give it away. The black hole's intense gravity attracts interstellar gas and pulls it into a faster and faster orbit. This heats the gas to billions of degrees, and it starts to glow. According to Einstein, this light wraps around the black hole, forming a circular shadow of the event horizon. It's a startling idea, but this glow is extremely faint. Shep can only see it if he uses two telescopes to zoom into a small piece of the event horizon.
So then you're effectively looking at a small swath of this image. So with one telescope pair, we can take essentially one cut through the shadow of the black hole. With many telescopes around the world, we can take multiple cuts through. We will be able to image this entire ring.
Shep has enlisted radio dishes in California, Chile, Hawaii, Mexico, and Spain. But these telescopes are still not far enough apart to see all the detail of the event horizon. To do this, Shep will need data from a telescope at the most extreme place on Earth, the South Pole. And one scientist has the responsibility of bringing this telescope into the system. Dan Maroney is a veteran of Antarctic astronomy.
At the South Pole, we'll be installing another mirror just like this, but we have to make sure that all the light that gets directed to it is hitting this spot.
In their lab in Arizona, Dan and his team are building an incredibly sensitive receiver to attach to the South Pole telescope. Once in place, the network will span the globe and will have enough power to image the entire event horizon.
This one sitting at the bottom of the Earth is really important to make sure that we can see as much detail as possible in the black hole.
Once built, it will take 3 days of solid travel for the team and the receiver to get to the pole. Then, they will face a battle with Antarctica's extreme environment as they try and fit the receiver to the telescope.
There's going to be a crane that they've brought down just for this purpose, and we will winch it up. We'll bring it onto the roof. We have to make sure this all works, but if things start to go a little wrong, yeah, there will be some added pressure on us to pull it all together. Hopefully, it will all go into place very nicely at the South Pole, and we'll be taking pictures with it.
With the addition of the South Pole telescope, Shep's network will truly span the planet. But to capture the image that proves black holes really do exist, he will still have one more massive problem to overcome. Shep's network stretches for tens of thousands of kilometers, but he must coordinate all the signals together within a fraction of a millimeter, or he'll end up with a fuzzy image.
Over the last ice age, as the ice receded, the Earth has begun to rebound a little bit. So over many years, the location of the telescopes actually changes a little bit. Even moving one of our telescopes by a millimeter is equivalent to shifting the entire focus of your telescope across the sky.
To overcome this, Shep uses a vast supercomputer called the correlator, which constantly monitors the exact position of every telescope in the global network.
This correlator is really one of the most important parts of the Event Horizon Telescope. It is what takes all the data that we've collected around the world and combines it together with great precision. We create a data set that's equivalent to having a telescope as large as the Earth. And from that, we can make an image of a black hole.
Once Shep gets this first ever image of a supermassive black hole, it will provide the strongest possible evidence that they really do exist.
To actually observe a black hole, to actually resolve the area around the black hole, that is the holy grail. That would be utterly amazing.
When we're finally able to see this distorted area in space, you know that it's real. Something that you've known was there, but you've never really been able to see before will be staring us right in the face, and that'll be a beautiful moment.
But if there really is a supermassive black hole at the center of the Milky Way, that creates a deeper mystery. What kind of influence could such a monster have over our galaxy?
You'll notice that we've stopped all of these slow-motion clips just before the moment of impact. The reason? To be honest, we think you should see the complete clips in the all-new series of Sports Science. Full contact sports and science collide. Head on. Sports Science, a new series. Tuesday on Discovery Science.
Scientists think there is a supermassive black hole right at the center of the Milky Way. And they believe our galaxy is not unique.
We're pretty confident that at the center of almost every galaxy in the universe is a supermassive black hole.
Relativity predicts that the intense mass of a supermassive black hole will bend space so much, stars fall into orbit. This has led scientists to think that black holes are vital in the formation of galaxies. But now they are asking if black holes also shape how galaxies evolve over time.
Galaxies come in many different sizes and many different shapes. They evolve differently over time, and that's been a mystery. Why should these clusters of stars have such different stories that play out? And it may be that what's lurking in the core, the hidden supermassive black hole, has something to do with that.
In the southern US, astronomers are tackling this mystery. Edmund Chung wants to know if black holes really do influence how galaxies change with time.
I wanted to really try to understand this process. It blows my mind to think about how that little thing could affect the entire galaxy.
His focus is a class of galaxy that has mystified astronomers: the giant elliptical galaxies.
This is a beautiful image from the Hubble Space Telescope of a giant elliptical galaxy. We know that these galaxies have a lot of gas in them. And the mystery is that this gas should produce a lot of new stars, but that's something we don't see.
Usually, stars form inside clouds of galactic gas. Tearing away their outer layers reveals black clouds of extremely cold hydrogen. Deep inside these chilly nebulas, gravity draws the gas molecules together to form spinning disks that suck in more and more hydrogen. Pressure and heat in the center skyrocket. Hydrogen molecules fuse, and a new star ignites. It's only in these clouds of cold gas that new stars form. Has something caused this process to stop in giant elliptical galaxies? Could this be a case of a black hole controlling the evolution of its galaxy? To find out, Edmund is using a telescope that revolutionized our understanding of the cosmos.
This incredible object is the Sloan 2.5-meter telescope dedicated for the Sloan Digital Sky Survey. What it did was it pointed at a particular region in the sky, and then over the entire night, it allowed the Earth's rotation to let it move across a strip. And over a course of a few years, we resulted in thousands of millions of galaxies observed.
Scientists turned these observations into one of the most detailed plans of the universe ever created. This gives Edmund a map of where to find giant elliptical galaxies quickly and solve the mystery of why they produce so few new stars. Researchers transferred the map to a giant library of aluminium disks. Each one catalogues a particular area of the night sky. Wherever the telescope detected light, the scientists drilled a hole. So, when Edmund looks at the same piece of sky, these holes line up perfectly with all the galaxies.
All right, boss, everything looks good. Ready to put it in? All righty.
By plugging separate sensors into each of these holes, he can see what is happening in hundreds of galaxies at the same time.
All the galaxies that we observe are about 500 million light years away from us. And this little fiber bundle covers an entire galaxy, and it collects the light, goes into this light gathering device, and then we look at it as scientists, and we can infer the properties of galaxies with this fiber bundle.
After a 2-year search, Edmund thinks a giant elliptical galaxy called Akira explains why these galaxies produce so few new stars.
You can see that it is red, very red, indicating that there's not a lot of star formation, which is the typical property of these giant elliptical galaxies.
Edmund's sensors picked up something strange deep inside Akira. A colossal wind of warm gas pouring out from its center.
So that's what we have here. So the red is the gas that's flowing away from us, and the blue is the gas that is flowing towards us. This
wind stretches for about 30,000 light years. The only power source that is able to generate this amount of energy is a supermassive black hole in the center of Akira.
Edmund thinks the supermassive black hole's eating habits produce this wind, and this warm blast prevents star formation. As matter falls towards the mouth of Akira's black hole, it forms a fast-spinning disk of debris called the accretion disk. Revolving at nearly the speed of light, it releases immense blasts of energy that push warm gas across the galaxy in massive gales. This galactic wind heats up the cold gas in star nurseries, and star formation stops. If the same thing happens in other giant elliptical galaxies, it might explain why they produce so few new stars.
It's just such a beautifully wrapped up story, and it just perfectly fits the idea that supermassive black holes are important, they are critical, and this is they are a necessary ingredient for galaxy evolution.
So we know that galaxies come in a great variety. We now think that there is probably a connection between that diversity of galaxy type and the fact that there are supermassive black holes in the centers. Those supermassive black holes, by virtue of their consumption of matter, can throw energy out that sculpts entire galaxies into different forms.
The black hole in Akira drives the evolution of the galaxy by feasting on something unexpected. It is eating dust and stars from its smaller neighbor, the Tetsuo galaxy. This is the start of a chain of events that will drastically alter both galaxies and their supermassive black holes. The galaxy's huge masses draw them closer together, allowing Akira to siphon gas from its neighbor. Eventually, the two galaxies will collide, then rebound, and collide again and again, causing mayhem, throwing stars and planets out of orbit and shedding gas into space until they finally merge to become one. Scientists think that galaxy collisions like this are actually very common. At this very moment, billions are merging across the cosmos. And these unions don't only affect the stars. The supermassive black holes also fuse together.
The merging of two black holes is a very violent process.
As those two black holes merge together, they spin faster and faster. They literally send ripples out in the fabric of space, gravitational waves.
One pair of colliding black holes exceeded by a factor of 10 all the energy emitted by all the visible stars in the observable universe.
These mergers may be violent, but they are a key way that black holes grow. And they can reach enormous sizes.
The most massive black holes that we observe are about 10 billion times the mass of the sun.
Today, scientists are discovering that when black holes get this big, even stranger things can happen.
This is home.
It is a very small world.
A little blue ball on the edge of cosmic infinity. From the tiniest grain of pollen
We are now beginning to understand the way in which we have to observe the Earth.
to the vast magnetic fields that protect us, Discovery Science puts our planet under the microscope. Earth Month, starts Monday the 3rd of April on Discovery Science.
Supermassive black holes are one of the strangest and most powerful entities in the universe. The ultimate prediction of Einstein's theory of relativity. They can grow to be hundreds of millions of times more massive than the Sun. And when they get this large, they can generate so much energy that they release huge jets. This is because black holes are messy eaters.
These black holes don't have very good table manners, and they burp out a lot of the material that's going in.
These are powerful emissions of radiation that come from the material that's falling into a black hole itself.
These jets can go for tens of thousands of light years. They're absolutely gigantic.
Scientists are investigating the impact of jets of this size and energy. Astronomer Grant Tremblay studies the jets given off by a black hole that has over 300 million times the mass of the Sun.
These black holes launch these extraordinary jets of plasma that shoot outward at near the speed of light. It's about 1 trillion atomic bombs per second worth of energy that's being dumped back into their ambient surroundings.
These powerful jets reside in the center of a galaxy with a truly bizarre structure.
So you're looking at right now at many massive galaxies. There are about 1,000 galaxies in this image. But at the very center of this region is one of the most massive galaxies in the universe. It's called a brightest cluster galaxy. And what you see here are bubbles. There's a bubble here and a bubble here. And these are not normal-sized bubbles. These are the largest bubbles in the universe.
These bubbles are voids in the gas that swirls around the galaxy. And the largest is so vast you could fit about 50 Milky Ways inside. Whatever carves out these voids must have massive amounts of power. The black hole's jets seem like the obvious culprit. But when scientists looked for further evidence, the mystery became even stranger.
If you look in this galaxy cluster in the optical waveband, where you can actually see the galaxies, you notice that the galaxy that's associated with these bubbles is different from all of the other galaxies that you see in this cluster. And it's home to this extraordinary 150,000 light-year long spider web of filamentary gas tied around these bubbles.
Inside these filaments, scientists could see young stars. How could a black hole's jets create such strange structures and drive the birth of stars? It remained a mystery until Grant's team made a breakthrough using data from a telescope called ALMA.
ALMA is an extraordinary revolution in science. That term gets thrown around a lot, but we really mean it with ALMA. It's a giant array of 66 dishes in the Atacama Desert in Chile, which is the highest and driest desert in the world. It is the world's most powerful eye to observe cold molecular gas. And cold molecular gas is the fuel for all of star formation in all of the universe.
The distribution of this cold gas gave Grant the vital clue to how the jet could drive star formation. As the jet of energy shoots out of the black hole, it pushes gas out of the way. Like a cosmic snowplow, it piles up the cold molecular gas. As this gas clumps together, it forms stars. This is how a black hole jet can drive the birth of new stars. It's an extraordinary discovery. In this huge galaxy, the black hole and its jets are not agents of destruction, but creation.
These supermassive black holes' interaction with their host galaxy is a far more elegant and subtle process than one might naturally think. Black holes, it turns out, can both quench or inhibit star formation, but at the same time, they can also trigger it.
This revolutionizes our understanding of black holes in the universe.
We now talk about a co-evolution of galaxies and the central black holes within them, wherein the growth of a black hole influences, in fact, the growth of the stellar population of stars around it.
It may influence the overall shape of the galaxy. It may help us understand why galaxies evolve differently over time. So instead of something passive, maybe black holes are more of an active sculptor of the galaxy.
Now scientists understand black holes like never. How they form, how they grow, and how they are active players in sculpting galaxies throughout the universe. These ideas agree with the equations that describe space and time. Einstein's theory of relativity. But to go further and reveal what happens inside a black hole, we need a whole new theory.
In the case of general relativity, it was used to predict the existence of black holes. But when you go inside that event horizon, although our physics predicted it, our physics breaks down inside.
The math starts giving you the kinds of nonsense that you get in a calculator if you put a 1 divided by 0, right? The calculator goes error, right? That's basically the math taking you by the lapel and slapping you in the face and saying, don't do that. That's not a well-defined operation. That's what happens to Einstein's math when you apply it to the center of a black hole.
This breakdown of relativity has led to fierce arguments about what happens inside a black hole.
This boundary of a black hole, the event horizon, may be a seething cauldron of activity. In fact, you would be vaporized, you would be fried if you were to go through it.
If you're a human falling in feet first, then there will be a big difference between the force of gravity at your feet and the force of gravity at your head. And this means that you'll get stretched out until you're super thin like a spaghetti. And we call that process spaghettification.
If gravity has been collapsing something down, smaller and smaller and smaller, does it ever come to a point that it cannot collapse any further from, a point of infinite density? And people have called that a singularity.
The problem is, in this world of the very small, the rules change. This is the realm of quantum physics. Only by combining these rules with relativity can scientists hope to understand what happens at the very center of a black hole. This is the Holy Grail, which scientists call the theory of everything.
Our belief is that the math goes haywire there simply because we don't yet have the correct mathematics. We have to take Einstein's ideas and merge them with ideas from quantum physics.
This is one of the final frontiers of science. But in Long Island, New York, there is a man and a machine that might help solve this enduring mystery.
Ever wondered what happens inside a black hole? What's it like living on the International Space Station? How did asteroids help shape the solar system? See the universe from the inside out. Strip the Cosmos. The new series, Wednesday, on Discovery Science. The Terminator. The Day After Tomorrow.
Behind us, right?
Close Encounters of the Third Kind. Independence Day. War of the Worlds. Deep Impact.
But this is no movie. There are no special effects. It's just Mother Nature at its most bizarre and terrifying.
Really in a state of emergency.
It's real and it's coming to a living room near you. Extreme Weather. Weeknights on Discovery Science.
Scientists have compelling evidence that supermassive black holes lurk at the center of galaxies. Here, they control and shape the destiny of billions of stars and planets. And these observations match the mathematics that explains space and time. Einstein's theory of relativity. But knowing what happens deep inside a black hole is a far bigger challenge.
Since you can't see in there, you can't go in there, or if you do go in there, you can't come back to report what it is that you found. It's purely mathematical. And the problem is, the mathematics that Einstein gave us isn't good enough to really tell us what's happening deep in the interior of a black hole. We have to take Einstein's ideas and merge them with ideas from quantum physics.
Quantum physics is the world of the seriously small. A strange land, swarming with subatomic particles like neutrons, muons, and quarks. Remarkably, there might be a way of understanding how these tiny entities behave inside a black hole. This could be pivotal in bringing relativity and quantum physics together in a theory of everything. An idea that could revolutionize how we understand the very fabric of time and space. On Long Island, New York, there is a machine that recreates the conditions inside a black hole. Bernd Müller operates the scientific equivalent of a sledgehammer. He generates what happens inside a black hole by accelerating gold nuclei to nearly the speed of light and crashing them into one another inside a detector the size of an apartment block.
We don't make a black hole in real terms. However, what happens in the collision of two nuclei is quite similar to what happens in a black hole. As matter falls in a black hole, it's crunched by the strong gravitational fields, and whenever you crunch matter, it also is unavoidable that it heats up. So here what we do is we create these temperatures in a lab rather than in the vicinity of a black hole. It is the hottest temperature in the universe anywhere. It's about 100,000 times hotter than the center of the sun. And in that case, we know that it's about 3 trillion degrees Celsius.
Each collision creates a state of subatomic matter, which scientists think exists inside a black hole. The trouble is, these conditions only exist for a yoctosecond, 1/1000000000th of a billionth of a second. Far too brief for Bernd to study. But he can reconstruct the conditions by what is left behind. Traveling at over 1 billion kilometers per hour, the gold nuclei crash into each other with incredible force and explode in a fireball of matter, raging at 3 trillion degrees. But within a yoctosecond, this scatters into an intricate pattern of subatomic particles. Its shape is key to understanding what happens at the moment of impact.
The collisions are extraordinarily violent. It's much more violent in a certain sense than a nuclear bomb going off. You have to shield them from a human being, because otherwise the radiation would kill you in a very short period of time. So that's why when the machine operates, you're not allowed to come even close.
Instead, the team monitor the collisions from the safety of a control room, half a kilometer away. By comparing the aftermath of millions of impacts, Bernd has built a picture of what happens at the instant the nuclei collide.
So this is a snapshot of the particles a few nanoseconds after the collision. And each different color represents a different type of particle. What we're interested in is how did the matter behave at and before the moment when these particles were emitted.
If Bernd can work out how to rewind the scatter patterns of these subatomic particles, he can get back to the billionth of a second after the collision. The point where matter is like that inside a black hole.
In a sense, this is very similar if you throw a stone in the lake. Long after the stone has dropped in and is gone, you see a ripple of waves moving out, right? The pattern depends on how big the stone was that you throw in, with what speed you throw it in. And so by analyzing carefully the wave patterns and tracing them back, you could determine in principle how big and what shape the stone was. And that's exactly what we're doing here.
Bernd needs powerful mathematics to do this. Equations that generate exactly the same patterns he sees in the collisions. These could offer clues to how science can finally unite the quantum world with relativity. And this could revolutionize how we understand the entire cosmos. After a decade-long hunt, he thinks he has found the right formulae.
This hot blob of matter turned out to be describable by string theory. And that's quite fantastic, I think.
String theory is a branch of mathematics on the very fringes of scientific understanding. But it is the prime candidate for the unifying theory of everything.
String theory is our most refined attempt to put Einstein's general theory of relativity, his theory of gravity, together with quantum mechanics. And the suggestion is that deep inside an electron or a quark, whatever, is a little tiny filament, a string-like filament that can vibrate, like a string on an instrument. And the different vibrational patterns, they don't produce different musical notes, they produce different kinds of particles.
This strange idea could offer our best chance of understanding how black holes really work. And this opens up new opportunities for our species. String theory predicts that black holes aren't really a one-way street. As well as pulling things in, they eject things out into space.
Black holes actually can radiate a little bit. They can send off particles that will emanate from the event horizon.
As black holes emit this radiation, they begin to shrink and evaporate.
An evaporating black hole emits so much energy that it could easily power all the energy requirements of humans here on Earth.
If we could find a way of dragging one down to Earth.
Is it viable? Is it something we can do? Not today, but there's no reason why technologically in the future we could not achieve this.
Even a black hole with just the mass of Mount Everest would release enough energy to power the entire planet. But there's more. As crazy as this sounds, string theory actually predicts something even crazier, deep inside the black hole. Something which offers mouth-watering prospects.
I only have an intuition like everybody else that we have a left-right dimension, a back-forth dimension, and an up-down dimension. One of the weirdest features of the math of string theory is that it does tell us that there are more than the three spatial dimensions that we all know about.
Inside that black hole, all these extra dimensions that may exist may give rise to a whole different version of reality, right? And some say maybe a whole other universe or a whole other infinity of universes.
And there's even the possibility that you might travel through a passage called a wormhole into another universe. Now, this leads to all kinds of interesting possibilities, like coming back through another wormhole to a time before you even existed or before your parents even existed.
They may be the weirdest entities in the universe, but if humanity can grasp exactly how black holes work, this could produce enticing new benefits for us all. And they offer a window to understanding string theory. This has the power to tell us how the universe works, both in the realm of relativity and in the quantum world. something that will revolutionize the way we perceive the very fabric of the cosmos.
They're right here in front of us, and our laws of physics don't work. They seem to stop time. Maybe they actually access different dimensions of space and time. So if we're going to understand these things, we got to get better at our game.
100 years from now, a generation of scientists will look back to us as the turning point, as the place where our understanding of space and time was one way before we grasped the nature of black holes. Then we stayed with these deep puzzles of black holes and solved them, and that caused our understanding of space and time to take a radical turn in a new direction, a direction toward the truth.